Hello, my name is Erik van Herwijnen. I worked for almost 40 years at CERN, and now I'm with MySys. In this lecture, I will go over the physics of shower development. So slowly we're getting closer to actually measuring the phenomena that we've been talking about in the previous lectures. I've split this lecture up in 3 videos. The first one is the introduction, which covers some material from the previous lecture. The second video will cover electromagnetic showers, and the third video, hadronic showers. So, what is this about? Well, we have an incoming particle, for example, as you can see in this picture, that comes with a certain amount of energy E, and it hits a block of material. And in doing so, it can interact in a number of ways. There's a number of processes that this particle can undergo, and a number of them will involve the creation of new particles. And if these particles have enough energy, then they in turn will create more new particles. And so you can have a cascade of particles all depositing a certain amount of the initial energy. And this then is a particle shower, and these showers, they leave measurable signals in the detectors around the block of matter. And so the challenge is then to, from the detector response S in all these different detectors or channels, to calculate the energy of the incoming particle. And in fact, this is what we call calorimetry. These devices that can do this are calorimeters, and so that's why it's important to understand the mechanism of the production of these showers. So what we mean by calorimetry is the detection of particles and the measurement of their properties, such as energy, through the absorption in a medium. And in fact, when this happens, all the particle's energy is converted to heat. The particle does not come out. It's lost for any future measurements. However, we cannot use temperature to measure this heat, because 1 calorie, which is the amount of heat that it would require to 1 gram of water by 1 degree, is actually equivalent to an energy of 10 to the 7 TeV. That's that's 7 orders of magnitude higher than the particles that we are making at the LHC. So instead, what we can do is we can measure the total energy that is deposited. We can also measure the position where this energy was deposited, and from that derive the direction of the particle that left this energy. And we can also deduce the type of the incoming particle. We can do some what is called particle identification. Now, the particles that traverse matter, they can lose energy if they're charged, if they have an electric charge, by interacting with the electric field of the electrons and the nucleons in atoms. Or if they're very energetic, or if they have higher mass, like hadrons, they can cause nuclear reactions, which can cause the breakup of the nuclei. And in both cases, they generate showers, electromagnetic and hadronic or nuclear. On this table, you see the most common particles that we have to do with in showers. The most abundant one are the photons. The neutral pion at the bottom there is the most abundant hadron that is made, because it's the lightest particle, the lightest hadron that you can make. And this has a very short lifetime, so it will decay immediately into 2 photons. And that's one of the reasons why these photons are so abundant. Then we also have other pions, charged pions, and they decay into muons. We have protons and neutrons, of course. And we have leptons, electrons, positrons, and muons. And you can see their properties in this table. That might be handy for you to, if you want to look at it, back at it later. We need some quantitative concepts to be able to describe the processes that make the showers. And these are the cross-section and the mean free path. The cross-section is the probability of an incident particle of energy E to interact with an atom with atomic number Z and atomic mass A. And basically, this is an area, it's a surface. So the incident particle is considered a point-like particle, and the atom is a sphere-like particle, and so the probability is the surface of the cross-section of this ball. And the unit that we use for this probability are barns, and 1 barn is 10 to the minus 24 centimeters squared. And this is understandable if you realize that the average size of a nucleus is about 10 to the minus 12, and so the radius squared would be 10 to the minus 24. The mean free path is the average distance between successive collisions, and that then is 1 divided by this probability, but you need to multiply that by the atomic density, so the number of atoms per volume unit, so you get the right dimensions of length. And from that you can work out the probability to interact and to survive, which is the exponential of minus L, the distance traversed in the material, divided by this mean free path. So the further you go in the material, the smaller the probability is that it survives, or the larger the probability is that it will interact. You can look at an example. In ship, for example, we have a very heavy target made out of heavy materials, quite a bit, and you can calculate how many protons will survive. The protons will have 400 GeV energy, and they will be delivered in bunches of, in spills actually, of 4 times 10 to the 13 protons. And if you work it out, then it turns out that 4.6 times e to the minus 5 protons will survive this heavy target. So all the protons get absorbed, they interact before they come out. However, if you don't take a 5 meter absorber but a 2.5 meter, then you can see that about 113 protons survive. And the whole point of this thick target is to make all the protons interact. Over 5 years, you can look at the total amount of protons that survive, and this is around about 345. So you can see that this very simple concept of the mean free path helps you to design the target of this particular experiment ship. Now we come to the charged particle interactions. You've had that in the previous lecture. There are 3 types important for the development of showers: ionization, deflection, and radiation. Ionization happens when the electron hits an electron in the outer shell of an atom, and most of the time when this happens, the electron gets ejected with a very low energy. However, since there are many of these electrons around, you can actually measure the signal and you can measure the energy that is deposited by ionization. If the energy of the electron is sufficiently high to cause secondary ionization, then we're talking about delta rays. For electrons, this will happen up to an energy of about 10 MeV. For muons, it's much higher. Ionization is important to energy of about 100 GeV. And for protons or hadrons, the energy that this is important is much higher, the order of TeVs. Then we can work out what the energy loss per unit path length is, dEdx electronic, the electronic stopping power, from a formula that you've seen in the previous lecture called the Bethe-Bloch formula. What is important is to note that it's very weakly dependent on the material, Z over A, but it's inversely proportional to beta squared, which is the fraction of the speed of light, and to the logarithm of beta squared times gamma. Then if you look at the deflection, this is an interaction with the electric field of the nuclei. And here, if the energy is large, the deflection is small. But if the energy is not so small, the deflection will be larger. However, the energy loss, mainly from the recoil of the nucleus, which is called the non-ionizing energy loss, will cause multiple scattering. And this is important for the resolution of not particularly of the calorimeters, but of other detectors where this would happen. And so again, analogously to the electronic stopping power, we have the nuclear stopping power, which is called dEdx nuclear. It has nothing to do with nuclear interactions. It's to do with the Coulomb interactions of the nuclei. And then finally we have radiation. As the energy goes up for the charged particle can interact with the Coulomb field of the nucleus, and instead of deflecting, it will radiate a photon. And for electrons, this is higher than 10 MeV. So this energy, the ionization, is taken over by the Bremsstrahlung. And the energy is called the critical energy. So dEdx elec equals dEdx radiative. The critical energy is proportional to the mass of the incident particle divided by the electron mass squared. So you can see that, for example, for muons, which has a mass 200 times more than electrons, the energy where Bremsstrahlung becomes important is 40,000 times higher than that for electrons. The mass stopping power is the material density multiplied by the stopping power. And on this graph you can see the mass stopping power for muons in copper. And you can see here, delimited by the vertical bands, various contributions to the mass stopping power, and the energy domains and the speed domains where this is important. And you can see in the center, for example, where ionization is important, the curve follows the Bethe-Bloch formula. And the Bethe-Bloch, since it's inversely proportional to beta squared, it has a minimum, and this minimum occurs at around 3 to 3.5 value of beta gamma, and after that it comes into a plateau. And particles that have that energy and that energy regime are called minimum ionizing particles. And their mass stopping power is about 1 to 2 MeV centimeter squared per gram. You can also see where the radiative losses become more important. that is the orange dashed line right to the right. And where it intersects the beta Bloch is where the critical energy is. And so there you can see the radiative losses are basically proportional to the energy. The red line contains the radiative losses of electrons, and you can see this is important for much lower energies. The radiation length, x0, is a quantity which is important at higher energies. So this thing does not make sense in the beta Bloch regime. And so what we saw is in the previous picture, dE dx radiative is proportional to E. And the inverse constant of proportionality is called the radiation length. It is x0. Since dE dx is proportional to E, that means that the energy follows an exponential power law, and it falls off as minus x over x0. So the radiation length is also the distance over which 1 minus 1 over E of the energy is lost due to Bremsstrahlung. The formula for x0 is given here on this page. It's x0 prime, which is x0 times rho, the density of the material. So this x0 prime has units of gram per centimeter squared, whereas x0 has units of millimeters or centimeters. You see both quoted in the literature. You have to convert between the two if necessary. Now we come to photon interactions. We have three types. The photoelectric effect, which is where in the low energy domain, an atom will absorb a photon and emits an electron. This was discovered by, or it was described by Einstein in 1905. The cross-section is very much Z-dependent, and it is inversely proportional to E to the minus 3. So in uranium it's important to much higher energies than in iron. And then we have Compton scattering and pair production. Compton scattering, which happens above the threshold where photoelectric effect is important, is when a photon hits an electron, an atomic electron, and it ejects it. It gives some energy to this ejected electron, and it continues with less energy. And so when it goes through matter, it will hit these Compton electrons successively until it doesn't have enough energy anymore, and then it will be absorbed by a photoelectric effect and it emit a photoelectric electron. And the cross-section for this decreases with the increasing photon energy. And yeah, so then the pair production, if the energy of the photon is larger than twice the rest mass of the electron, remember that's about a half MeV, so in total 1 MeV, then in the Coulomb field of the nucleus, you can get a pair product. The photon can pull an electron and a positron out of the vacuum and create an E plus E minus pair. And the Feynman diagram for this process is just it's an inverted Bremsstrahlung. You swap the photon and the electron, and then you get pair production. From the previous lecture, you know how to calculate the cross-section from these Feynman diagrams. So if we look at the energy scales of these photon interactions, we see at the bottom photoelectric, then Compton, and then at higher energy pair production. For heavy materials, the Compton-dominated area is much smaller, as I explained. Then there's an important relation between the radiation length and the mean free path, because the cross-section for pair production turns out to be inversely proportional to the radiation length. And so it is related to the mean free path, as we saw before. And therefore you can work out the photon survival probability at a certain depth. And to make this handy, we have something called the attenuation coefficient, which is inversely proportional to the radiation length. So radiation length is a characteristic length for both bremsstrahlung and pair production. And it's a central quantity for describing the longitudinal development of showers. Finally, so the difference between photons and electrons. Electrons lose energy in a continuous stream of events in which atoms are ionized and bremsstrahlung photons are emitted. Photons can penetrate matter a considerable amount of time without losing energy and then interact in a way that they completely change their identity. They become an E plus E minus pair. So here's a quiz. Just go over the questions, check that you understand and that you could answer them. If not, go back to the material and you will find the answer in the slides.